Hello, my name is Professor Hudson, and you are viewing narrated PowerPoint lectures for section 12.5 of chapter 12. Let us continue discussing what are mutations and how do they occur. In the previous segment, we talked about how the loss of chunks of DNA, or inversions, or duplications, or translocations, or deletions of DNA can affect protein function and cause different syndromes. We also talked about more common situations, such as when 1 to 3 nucleotides at a time are altered. Let us talk a little bit more about that situation. Effects of mutations on protein activity. Point mutations. So as mentioned previously, a point mutation involves a change in a single DNA nucleotide. The effects on proteins vary. A single nucleotide change can result in a non-functional protein with a premature stop codon, which we call a nonsense mutation at the level of the protein. You can end up with a protein that functions, but not the way that it should. And we refer to this as reduced functionality. And we call it a missense mutation at the level of a protein. Or you can have a situation where you can have a change in a nucleotide that the DNA is changed, but the protein is ultimately unaffected. And we call this a neutral or silent mutation at the level of the protein. Point mutations are typically considered to be substitution mutations. This is where no nucleotide is deleted and none is added. However, a nucleotide that is there is changed to something that's not supposed to be there, hence the substitution. You can also have what we call frame shift mutations. This is a situation where you have a point mutation, which would be a single nucleotide addition or deletion, or possibly 2 nucleotide additions or deletions. When 1 or 2 nucleotides are either inserted or deleted from DNA, the reading frame will change. Remember, the ribosome moves along the messenger RNA, reading the nucleotides and the codon in sets of 3. If 1 or 2 nucleotides are inserted or deleted, this will throw off the sets of 3 that the ribosome is reading. The protein is almost always rendered non-functional. In this example below, it shows you, let's say we had a sentence that normally read, "The cat ate the rat." Let's say we deleted the letter C from cat in this sentence, and then regroup the letters in sets of 3. Then the sentence would read, "The atta tet her at." Notice just removing that one nucleotide or that one letter in this example threw off the reading of the sentence. The same situation in an insertion. Let's say we inserted an extra C in front of the word cat. Then the sentence would read, "The ka tat eth era tat." Basically, deleting or inserting one extra letter in this sentence turned the normal sentence into gibberish. This is what happens when nucleotides are inserted or deleted from DNA. The messenger RNA will be affected, and ultimately the protein will be affected. This slide is just showing some examples of a base substitution. Remember, the base substitution is what we most commonly think of as a point mutation, because it's just a single nucleotide that has been changed from one thing to another. The reading frame is still maintained, however, you can have either a missense, a nonsense, or a neutral, aka silent mutation at the level of the protein. This figure also shows what happens when you add or remove a single base. Remember, we say that is an addition or deletion, and those are typically considered in the category of a frame shift mutation. Let's look at an animation that shows mutation by base substitution.
A mutation occurs by base substitution when an incorrect base is incorporated into DNA. Some base substitutions occur because purines and pyrimidines exist in two structural forms. The most common form results in base pairing between adenine and thymine and between guanine and cytosine. However, the hydrogen atoms can move to form a base with altered hydrogen bonding properties, creating a tautomeric shift. When a tautomeric shift occurs in adenine, the adenine can bond to cytosine. A tautomeric shift in thymine allows it to bond to guanine. This error in DNA replication is passed on to the cell's progeny. The change in a single nucleotide in the DNA results in a change in the corresponding nucleotide in messenger RNA. The change in the codon can result in a different amino acid being incorporated into the protein.
Now let's look at an animation showing addition and deletion mutations.
The nucleotide sequence in DNA determines the nucleotide sequence in messenger RNA and, consequently, the sequence of amino acids in a protein. A mutation in the DNA can result in a change in the amino acid sequence of a protein. One type of mutation that can occur either spontaneously or as the result of a mutagen is the addition of one or more nucleotides during DNA replication. Because translation of a gene begins with a specific codon and proceeds one codon at a time, the addition of an extra nucleotide shifts the codons in the mRNA. This type of mutation is termed a frame shift mutation. A frame shift affects all amino acids incorporated beyond the original site at which the addition occurred. If the new codon generated by the frame shift is a stop codon, the protein synthesized will be shortened and is often non-functional. Another type of frame shift mutation occurs when a nucleotide is deleted during DNA replication. Deletion of a nucleotide in DNA results in a change in the codons in messenger RNA from the point of the deletion and changes in the amino acids inserted into the protein.
Now that we have completed chapter 12, let's take a look at chapter 13, which deals with gene expression and regulation. This chapter also discusses mutations in additional detail. My name is Professor Hudson, and you're about to view narrated PowerPoint lectures for chapter 13. The topics that we're going to talk about in chapter 13 are how do mutations affect protein structure and function, and how is gene expression regulated. This is actually a continuation of chapter 13 in terms of understanding the transition from DNA to RNA to protein that was covered in module 6, part 1 on the central dogma. Let us begin. DNA replication occurs prior to mitosis and meiosis when cells are about to divide. During DNA replication, DNA polymerase mismatches nucleotides once every 1,000 to 100,000 base pairs. Yet the completed DNA strands contain only about one mistake in every 100 million to 1 billion base pairs. So DNA replication, the final product, the DNA has very, very, very few mistakes. In humans, there are typically less than one error per chromosome per replication cycle. This reduction in errors is accomplished by DNA repair enzymes, which proofread each new daughter strand and replace mismatched nucleotides. Proofreading occurs during and after replication. Toxic chemicals, radiation, and occasional errors during DNA replication can cause mutations. DNA is altered or damaged in a number of ways. Mistakes are made during normal DNA replication. Certain chemicals, such as cigarette smoke, can increase DNA errors during and after replication. And UV radiation or X-rays can contribute to incorrect base pairing. Some mutations are harmful, and an organism inheriting them may quickly die. Some mutations may have no functional effect. And some mutations may be beneficial and provide an advantage to the organism in certain environments. These advantageous mutations may be favored by natural selection and are the basis for evolution of life on Earth. We talked about mutations in Chapter 12, but Chapter 13 discusses them in more detail. Let's just review the types of mutations discussed in the previous chapter. Mutations range from changes in single nucleotide pairs to movements of large pieces of chromosomes. An inversion occurs when a piece of DNA is cut out of a chromosome, turned around, and replaced into the gap, as illustrated in this figure. A translocation occurs when a chunk of DNA is removed from one chromosome and attached to another, as illustrated by this figure. Nucleotide substitutions, often called point mutations, involve changes to individual nucleotides in the DNA sequence. One type of point mutation occurs when a repair enzyme finds a mismatch but mistakenly cuts out the correct base and puts in the complement of the erroneous base. Effects on protein vary from producing a non-functional protein, we call this a nonsense mutation, a reduced functionality protein, we call this a missense mutation, or the protein could be unaffected, which is a neutral, aka silent mutation. Non-functional nonsense mutations usually result from a premature stop codon. We also talked about insertion mutations. These occur when one or more new nucleotide pairs are inserted into the DNA double helix. This can cause what we call a frameshift mutation. And deletion mutations occur when one or more nucleotide pairs are removed from the double helix. This too can cause a frameshift mutation. In both cases of the insertion and the deletion, the protein is almost always non-functional. This figure is just illustrating the effect of different types of mutations on the hemoglobin gene. As you note from some of these mutations in this figure, some of the mutations turn out to be neutral at the level of the protein, i.e., the protein remains functional and normal with the correct amino acid even with the nucleotide change. You can see this with mutation 1 and mutation 2. However, there are some situations where the mutation gives you a reduced functionality protein. In this slide, it's showing you mutation 3 gives you the mutation you see with sickle cell anemia. The protein functions but not as effectively. Okay. And then with mutation 4, they show you that you end up with a premature stop codon, and then the protein is completely non-functional. And thus you can end up with the disease beta thalassemia. In the next segment, we will talk about gene expression and how gene is regulated.